Okay, we'll get started. That was some minutes lost because of some setting up the Zoom thing. So good to see most of you in person. I know some of you are still traveling or are probably sick, so I hope you guys recover. I haven't shared any screen, so this is fine. But okay, so first of all, we are in IDS 575, right? So if somebody is in the wrong classroom, this is a good time to check. Okay. So folks who are remote, in case you don't see the full set of slides, let me know. How, actually, I need to check the chat. Let's see. Okay, I assume everybody can see. So if somebody is on Zoom right now, just let me know if you're not able to see the slides. Share the slides. Okay, this is also not needed. Okay, so welcome. This is second lecture. I know we have lost a week last week because of the holiday last Monday. But it's okay. I mean, we'll set a pace and maybe speed up some things that you've seen in 572 and so on. Okay, I don't have much administrative things to say, except assignment 1 is released. You will access it on the GitHub page. It's just a folder within which you can get a Jupyter notebook. If you don't know how to work with a Jupyter notebook, contact us, me or the TA, or even during the break, I can let you know. But right now I don't want to switch tabs, so I'm gonna continue with the lecture material now. So assignment 1, as I said, is out. Take a look at the questions. I think most of you have formed groups. Folks who have not formed groups, you probably just got an email from the TA. Do form the groups soon. Especially, if you form the group now, you can at least get started on the assignment. It is a long assignment, and it's quite open-ended. It's a little bit different from maybe what you've seen in 572 or some other course, but that's because that's how it is in real life. Okay, things are not spelled out exactly where you just need to fill in the blank. Okay, so it's a little bit more open-ended that way. So let's see how you do. If you are proficient with Python, it's going to be super easy. If you're not, then it's going to be challenging. Okay, so I guess it's due on Feb 5th or 6th, one of those days, right before the. So it's a Sunday before the next that class. Okay, during that week. So you have 2 weeks to finish that. Okay, so with that, that's the only administrative detail. Do you guys have any questions about administrative things? Otherwise, I'll get started on the material. No questions? Okay, so one last administrative piece is that we do have recordings for the lectures. You should automatically access it on Blackboard. So first lecture, if in case you want to look at a particular part that was not clear, you can just go look over that. Okay. So with that, let me get started. I don't know most of your names, but hopefully through the course, over the next few weeks, I will learn them, and hopefully let's keep it interactive. So if you have questions, interject me. So okay, with that, let me actually do a quick informal poll in the classroom. Sorry about the folks who are remote. So how many of you have done already 572? Okay, who has not done 572? I guess that's, so this is your first machine learning, I guess, let's say core or basic course. Is that correct? Okay. So folks who have not done, you are the key audience here, because people who have done 572, they kind of they know some of these topics. So in case I'm getting through something and nobody's responding, doesn't mean that rest of the audience doesn't understand. Okay, just that sometimes they might have seen this material before. Okay, so people have not done any introductory machine learning course before, I strongly suggest pause me. Okay, and that's how it's going to be interactive. Otherwise, it's going to be monotonous thing where you'll fall asleep. Okay, I mean, I will fall asleep if I was in the audience, so certainly you will fall asleep. So with that, let me get started. This is lecture slide number 2A. I'm starting with 2A instead of 1B because 2A again does a little bit of recap and ramping up. So that's why I've started from here, but I'll skip over to 1B. And I'll tell you what the content is. We covered KNNs and we're gonna get up to that and then talk about decision trees again today. And for some of you, it may be revision, but you have to be very precise, and hopefully you'll enjoy that treatment review. Okay, so yeah, so I mean, I'm just gonna do a quick recap. This is just so that it sets the pace for the median audience. So some of you are super enterprising and super smart. So for you guys, it's just bear with me for a second. So what's the objective of this course is to establish the theoretical gaps. Okay, so you want to have a little bit of formal language when you talk about machine learning. It cannot be just, hey, plug and play XYZ model into XYZ data set. That's informal, but you want to kind of formalize it. Okay? As a profession, you cannot just do very ad hoc things, right? So the field is maturing over the past 2 to 3 decades, and so you want to have a little bit more, I guess, professional treatment of the subject. And so that's the objective of this course. So basically solidify some underlying foundations. Okay, and foundations in particular, we are only pretty much looking at statistical foundations. And so for that, we'll need a few prerequisites. And so, but in contrast with 572, this is actually a little bit, what's called theory, but it's not really theory in the academic sense. Okay, academic sense theory means something else. Here, theory just means we're not very deeply embedded into idiosyncrasies of any data set. Okay, we don't really worry about that. We really care about the idiosyncrasies of each model and technique and choice that we're doing. So we're at that level. Okay, so that's where we want to fill the gaps. And so the application parts, hopefully, in the first assignment you'll see some applications, but you'll get the feel for applications in the homework and the project. And project components is huge, by the way. It is 30% of the grade. Or maybe 35%. So that's where we'll kind of really get deep dive into an application. So in terms of prerequisites, so when I said foundations, when I say statistical foundations, it's actually not some huge delta. Okay, and in fact, the core course is designed such that it's not a completely like you're not learning Greek or Latin here. It's something that you're already familiar with, but you do need these basics, and it's just a mixture of those basics that's the foundation. Okay, so it's just if you're already quite strong in calculus, linear algebra, basic probability, and Python, this class is going to be a really good, mixture of them. And so you'll be, it'll be easy for you, but at the same time, you'll know exactly what parts you're exercising when you deal with, ML modeling, right? So the outline for today is recap lecture 1. In fact, in lecture 1, we kind of did not talk about decision trees, but we'll get there. And then today's, lecture 2's content is supposed to be linear regression and least squares. And these are all foundational topics, basic, from one perspective. At the same time, it could confuse you. So let's look at them together. So this is, again, motivation. I don't think in 2022 we need too much of motivation with the relevance of machine learning and data and computation in general. Okay, so let's actually get back to at a very, very, very high level, 20,000 feet view of what is machine learning. It's basically building a box, a component, and that component is essentially a function. So if you've done Python or any other language for that matter, methods, right? So you can just think of one of the artifacts that your machine learning effort or process or whatever you spend X hours, let's say 10 hours or 100 hours. At the end of the day, you need to produce an artifact. That artifact is generally this box. That box is essentially a function. Okay, so def my function with some inputs. The input is exactly X here. I represent it using variable X here, and then produce some output. That's one most popular, I guess, artifact of machine learning. And And here we are saying a math function, but really it's a function. And those who have done a little bit of calculus, that's exactly what it is. But inside the definition of the function, you can do hundreds of different things. You can use all sorts of primitives that you know from programming. You can do for loops. You can do if else. You can do multiplications and whatever computational things that you know. Okay. So here's a quick example of a table. This is just motivation. This table is basically like an Excel sheet. So some of you who have quite a bit of experience with Excel are spreadsheets, right? So these are just a bunch of columns, and each row corresponds to an observation or an example. So the data set D is basically the collection of all these examples arranged in a row-wise manner, and the ith row is represented as X superscript I and Y superscript I. Okay. So 10th row is X superscript 10, Y superscript 10, and capital X is not capital X is something different. It's the input space. Okay, so the word space should remind you if you've done a refresher on linear algebra, input space, vector space, vector space, sorry, right? So it's a space. Okay, space just basically for us means a set, a collection. So all these possible features or all these possible feature vectors, they all reside in the same space. Okay, so you can think of X as a vector space if you want. If all the coordinates of X are, or all the attributes of X are numeric, then you can just think of that as a vector, and capital X is a vector space. Okay, and similarly, Y is an output space. As I said, these are, when you think of a space, it's just a set, but space means it's endowed with a few additional things like distance metrics and so on. So it's a set. So you can see, it could be a bunch of strings, or it could also be numeric. Okay, so there's just to define input space, output space, attributes, features, and the notation D for the data set, and superscripts for the observation index. Okay. Okay, so in this grading example, in this table, basically what we want to create is a function which predicts the grade of any person. Let's say this entry given these features, okay, attributes. So that's one version, I guess one popular problem in machine learning. Okay, and that is called supervised learning. So in supervised learning, ideally you want to have some training data where you already know the labels, and so using that training data, you will condense that into this function f, and you give this function to anybody else. They can use that function. It's a function, so they can pass a function input x, and they can get an output y. Okay, so they can always evaluate it later. And last time we saw the thing in red. It's called instance-based learning, and we discussed k-nearest neighbors. Okay, it's an extremely strong technique, actually, although not many people will see it, highly talked about, but it's actually a very good first hammer to use. And we'll see why it may not be a good choice, especially, for example, when you have lots of data. Okay, too many rows, then unless you do some additional computational tricks, it just takes too much time. Okay, so here's another, here's a list of all these techniques. We'll actually spend quite a bit of time on each one of them, and some of you probably already know most of it, if not all of it, or some of it, especially from 572 perspective. So you should certainly add to discussion, if something is not correct or something is too simplistic, the way I'm explaining it, you should add your points. Okay, or if something, if I'm skipping over something, please chime in. So, okay, so today, as I said, we want to cover the first three. I mean, we want to reach cumulatively with this, at least, let's say, till linear regression, not logistic regression. So we're going to try to cover decision trees and then linear models. Okay, okay, so here's a visualization, and we'll see this type of visualization quite often. Here, actually, number of attributes is only, the number of features is only one. Okay, so it's just x is one dimensional, and the output. Oh, sorry about that. So this is not a good access label, but there are two features here, x1 and x2. Think of it as two columns in your table, and then the colors represent in this case, grade. Okay, so for example, red means 1 grade, green means 1 grade, and blue means 1 grade. So the colors are the grade, and the data points, the circles just mean, hey, x value is something and y value is something. And those two are just two features. Okay. And prediction is mostly given a new black data point for which you don't know the color, guess the color, guess the grade. Okay. Is the extreme basics clear? I mean, anybody who some of you don't have, I guess, I don't know if you have the right background or not, but I want to have everybody at least comfortable with the way I'm talking about the black box of function. Okay. Some of you must have done programming, at least here, if not before. So you should just think of, if you like the programming perspective, at the end of the day, it's just a function. Okay, it's like def my function with some input, okay, arguments. So now let's talk about k nearest neighbor. It's actually a first assignment requires you to build a KNN algorithm or the model from scratch. So you will be able to write and understand what you're adding, what you're comparing, what's the nearest neighbor, and so on. So let's recap. Let's say there's a training data set with 20 points. And let's say we just chose k to be 9. Okay, I mean, this is whether it was 9 or 3, doesn't matter. And let's say query x prime. Okay, so x prime is a query because we're using a prime only because it's not part of the training data set. Is this 4 tuple? A 4 tuple is just, I mean, tuple abstract data type you must have seen in Python. So this 4 tuple has just 4 values for the 4 columns, basically 4 features that you have. I don't remember the column names, but these are the 4 values that it's taking, categorical values. And given that, you want to make a prediction y prime. Okay, so y prime is what your function returns, given the input x prime. And this messy notation, I would say initially it looks pretty messy, but it's just a shorthand. Okay, so I think from regular English, when you type on Twitter, you use shorthand. Similarly here, we're just using a shorthand instead of writing in English. Argmax of y in y, y in the set capital Y just means pick the argument of whatever is maximizing the thing inside the brackets. Okay, so it's like if you have used NumPy, and NumPy is also, by the way, something that you will try out in assignment 1. If you have used NumPy, you can find the maximum element in your array. Okay, so it's basically not just maximum element, but index of the maximum element. That's kind of what we want here. So that's what is given by argmax. Okay, so if you have 3 numbers, 5, 10, and 15, and if you take argmax of that vector, then it will be 3, index 3. Or if you use a 0 indexing like Python, it will be 2. Okay. Any questions there? Okay, so what is the prediction here? It's basically saying step 1 is to, so there is some extra symbols going on here. So this sigma notation is like a summation notation. It just means summation. Okay, and you may see an abuse of the same, abuse of the same sigma symbol here for, let's say, covariance matrix of a Gaussian distribution, multivariate Gaussian distribution. We will disambiguate that when we get there, but here it just means summation. Okay, sum over all indices i's, all my data point indices, also basically observation examples, such that they are the neighbors. They belong to the k nearest neighbors of x prime. Okay, that's all it means. So it's a shorthand. You can always write the same thing in 3 sentences. Okay. Whether you prefer the shorthand or whether you write English version of it, it's fine. But you have to treat it like a professional way. You can't be very ad hoc in your description. If you stick to English, that's fine, but you have to be precise what you're doing. So it's just saying sum over all the those observations which do belong to the k nearest neighbors of x prime. So there has to be k such points ideally. And yeah, so you pick those points and then you look for, so this is, I think last time I was explaining, this is just an indicator function. So it's again a shorthand. It's just saying, hey, what are the possible grades, right? So remember y, this output space y was a set. It had A, B, and C, 3 grades, right? So it's just saying, okay, out of these k nearest neighbors that are found, there would, some of them would have grade A, some of them would have grade B, some of them would have grade C, right? So it's just saying how many of them. This indicator is just saying, hey, does the ith one grade, is it equal to, let's say, grade A? So let's fix the little y on the right hand side to be A. It's just checking which of these k guys is grade A, and for that situation, indicator is going to give a value output 1. Okay? As I said, it's a function, so it has some input, it has some output, right? The input is each of the k observations is y label, output label. I'm just saying, hey, is it equal to A? Then output 1. If it's not equal to A, output 0, and you sum it up. Okay, so you're just counting for grade A, how many of them are the same as grade A, and so you count them. So let's say three of the k nearest neighbors are grade A, so your output, your function after doing the summation is equal to 3. Okay. And similarly, if you're grade B, then maybe 2 of them are grade B, so your summation output is 2. Okay, so that's what's written in a shorthand way. There's a reason for doing that like this, because we're going to next introduce a similarity function. Okay, and that's why we want to retain this form. Otherwise, you could write it in a slightly different, maybe different ways as well. Okay, so it's just count the number of number of these k nearest neighbors which conform to each of the output class, output value A, B, and C. Maybe the counts are 3, 2, and 1. Then the argmax is 3, 2, and 1. If you think of again the argument of the maximum, so 3 is the maximum, argument of the maximum is the first index. Okay, so that's what we're returning. Of course, you want to map it back to the actual value of y. Maybe you look up what the first index corresponds to. Maybe it's grade A. You return grade A. Okay. Is that clear? Anybody having a question here? Okay. Please ask questions. Okay. Just because nobody else is asking questions, 99% of people are not asking questions doesn't mean anything. It's the whole point of us having classroom interaction and you not just looking at YouTube or Coursera or something is that I'm here to, the teaching staff is here to design with. Okay, so don't worry about the rest of the people whether they understand or not. You please ask questions. Okay, so I guess I already explained this. Yeah, so I guess this is a pictorial way of saying, because k was chosen to be 9 in that running example in the previous couple of slides. For the black dot, you just find the nearest 9 points, and whatever the colors are, you can see that the green one is actually has a count of 4, red has a count of 3, and blue has a count of 1. And so you based on those counts, you kind of say, hey, the black dot should have a color green. Okay. I guess, yeah. Is it 5 somewhere? Oh, is it 5? Okay. Yeah, so these are the counts. Okay, so when I made the example, I chose some different numbers, but in this example, if you want to correspond to the figure, grade B has the, B which corresponds to green has 5 dots in the nearest neighbor, 5 colors that you see in the nearest neighbor. So that's why the output is B. So given this, now it should be very clear, right, how to write this as a Python function. Okay, you just need to have access to your data set, so that when the function is given an input vector, or let's say tuple, or it could be a numpy array, this 4-dimensional thing, and then you should be able to compute the nearest neighbors, then compute these counts, and then pick the argmax, and then return the appropriate class. So that's kind of clear. So these are the steps that you need to do inside a function, as long as the function has access to this data set. So that's why it's lazy instance-based learning. So it's not creating any, it's not doing anything beforehand. Only when you query something is when it looks back in the data set and figures out what the actual label is, right? So here's a version which is introducing the similarity function. Okay, so look at the first line, which is what we kind of discussed in the previous slide. Instead of that, you can have a weighting. Okay, so weighting is just for each. Remember, we are just counting here how many greens are there, right? How many greens are there? How many blues are there? How many reds are there? right? Instead of counting, think of assigning a, so the counting was because if let's say there were 5 greens, each green point was given like a value of 1. Okay? And so that's why 1 plus 1 plus 1 plus 1 plus 1 is 5 for green. And each of the rights were also given values of 1. So that's why the sum is 3, and blue also, value of 1. So that sum is 1. So instead of those values, what if I change those? What if I put different values? Instead of 1, 1, 1, 1, 1 for 5 green values, what if I put 2 for something which is super close to the black dot? And what if I put, let's say, 1 to something which is, maybe 2 units away from the black dot? Okay. So I can increase the value of the dot which is the closest to me, and decrease the value of a dot which is a little bit further away from me. And that's the effect of so that's basically weighting. And that's exactly what we're doing here with this k function. Okay, it's just, so remember also the k function cannot it's a function of only the input features. Okay, so it's xi and x prime. So based on where the dots are, so in the 2D plot, those are the two features. So where the dots are determine how much k should be. So for example, if the black dot is exactly overlapping on the green, think of the k value here is like super high, maybe 2 units or 20 units or whatever. And if the black dot and the green dot, for example, is much further away, you can just change it to some lower value. Okay, and that's it. So you're just it's just a weighted sum, and there is no other change. And again, you take the tally up, take the maximum, sorry, take the argument of the maximum. Okay. Yeah, I guess here we change the set to k is equal to 3, but same idea applies. Any questions about this part? So here, when k is equal to 3, you can see that if we did not do weighting, then the grade would be, let's say, the grade corresponding color red, which is different from when k is equal to 9. So your k influences what you're predicting in this, in the illustration. But also, of course, if you want to, but you can see that maybe let's say if you're going to be very, another way to look at this is basically that the black dot is, has a high amount of overlap with the green dot. So perhaps the weight on the green dot should be higher. So the similarity is higher. And so that can overpower the weighted sum that you can get for the red color. So you can still predict green if your k is such that, you have a higher, number for the green choice. Yeah, so I guess it's here 10 versus 3.5 and 3.5, so it's still green. It's still grade B. Okay, so one additional thing that you need to do, the same idea doesn't work when you have to make a numerical prediction, because there's some normalization that you need to do. And so what is that normalization is that, first of all, so there are two things you need to do. First is there's no need for an argmax, because the output has to be a number. Okay, so which means they need to average the numbers corresponding to your nearest neighbor examples. So what do you mean by that? The first change is that instead of an indicator of whether the ith example is equal to ith example is equal to one of these colors. Okay, you just directly use the ith example's value. So there's no colors anymore. There's no 3 colors or 2 colors anymore. Okay, it's just an output which is numeric. So 10 units, 12 units, 12.5 units, whatever it is. So out of the k nearest neighbors of x prime, maybe there are so these, out of these k nearest neighbors, there will be corresponding numbers. Okay, you're just gonna basically average them. Okay, but you're not going to average them equally. You could average them equally if this similarity function was like identity function. Okay, I mean, in the sense that it was always written 1, for example, then it will be just the sum of yi's of all these nearest neighbors. Okay, that makes sense, right? If there are like a few points around you and they're all valued at 10, 10, 10 units. For example, think of pricing a house, right? If all the neighborhood houses are same price, let's say, then your house probably will also be the average of those prices, and let's say that's the price. Okay, that's one prediction, right? But here K is again going to modulate the same way it modulates the outputs for the classification case. But what you're doing is, instead of this indicator business and taking an argmax, you're just directly using the value of yi. And you also need to take into account that whatever you have used in the numerator, these K values have to be also, summed up in the denominator. Okay, and that's to keep the average, at the same scale. Okay, so actually, this is a good time to experiment with document camera. So let's see. Not here. I don't know if they can see the document camera. Is anybody on Zoom right now? Okay, it don't have to be, but if you are, then let me know. Let's see. So this is actually a very simple example. So let's say the colors here. Should increase the font size. So let's say there are 4 numbers. Let's say 4, 1, 10, and 2. Okay. Oh, this is inverted, right? Oh no, you're not seeing. Okay. How is this working? Let's see. It's actually inverted, right? So how do I flip it? Okay, so all I mean is that if you think of the regular averaging, right? No, what happened? It's not on remote. Okay. Let's see. Share the screen for this, but it didn't work earlier. So let's see. Yeah, so that I don't know if it's just as simple as changing doc cam. That's not working. Alt time to switch. Okay. No, that doesn't work. Well, it's okay. I mean, this is just a 30-second thing. So let's. Yeah, I just want to illustrate a very minor thing, so it won't take much time. So basically, the first average is, since there are 4 numbers, it's 1/4 times the first number plus 1/4 times the second number, and so on, right? So these are the weights, okay? They are equally weighted in a regular average, okay? All we're doing is, instead of 1/4, let's say you do 2/4 of A, then you've already used up 2 units out of 4 units that you could allocate. So you, for the remaining 3 numbers, you have to use 1/2, right? So so 1/6, yeah, 1/6b plus 1/6 times c plus 1/6 times b. Okay. So now these weights are unequal weights, okay? And this is exactly what the K is doing. So just for those who, so how many did not follow this? Just the analogy between regular weighted averaging and, yeah. Oh, first of all, so first average is clear, right? It's just an average. Take a bunch of numbers, and in fact, if you select in Excel a bunch of numbers, you'll see the mean in the bottom, right? It'll just directly show it. So weighted average just means you're changing the weights, okay? The ones I've circled here. They still sum to 1. Okay, you can check that, right? So 1/6 times 3 is 1/2, those 3, and then 1/2, one more, and so they sum to 1. It's just that those weights, the total unit of 1 is just split between inequally between the numbers that are getting aggregated. That's all. So this is what is happening in that KNN definition, in the KNN estimate. Okay. So nothing much going on here. Let me switch back to this. I don't know. And the regular camera is not working. Probably. Yeah. No idea. I hope they can see this. Okay, so for remote folks, all I was trying to illustrate was that this k. I just chose some example values of k, and I was just demonstrating what this why this normalization is needed. Okay, that's all. So okay, so now KNN previously whatever algorithm we wrote, it can also address the regression case. Regression case is when your output is numeric. Your output space could be the real numbers, for example, right? Instead of a set of just A, B, and C values, A, B, and C classes. Okay. Yeah, here's a quick illustration again. So with these three numbers, you're gonna just take the weighted average. So the weights are here in this illustration. It's for red points because they're further away. It's 3.5 units in this illustration, but you have to decide what the right weight is, and that should be somewhat inversely related to the, for example, the Euclidean distance in this case. Okay, so the Euclidean distance is just coordinate-wise differences. Square them, take a square root. That's the Euclidean distance between 2 points in 2D space or in in a vector space. And so similarity, which is what k should be, is somewhat inversely related to that. Okay, so you can do some number minus that distance, for example, or you can do some other ways to say when the distance is large, similarity is small. That's what you want to achieve. Okay, yeah.
So which distance measure would be using when we have categorical features?
Oh yeah, I mean, if you have categorical features, then you have to define an appropriate distance measure. So we haven't discussed it in this so far. One way to you can just have a simple indicator. So what is the name of the measure? I'm not sure if having distance is the right name, but you can use some, you can define your distance metric. Okay.
So we have to hard code the distance and then
you would know what is the categorical values in that particular coordinate, right? So for example, I think in the grading example, there was like for example, the homework column, there were some 3 or 4 levels, 3 or 4 categorical values. Now, if two people have different levels of that 2 different values of the homework, and let's say there is, I mean, actually for that illustrative example, there is an ordinal relationship between homework effort, let's say, or even the exam score. Even if there is no ordinal relationship, which means that higher effort or lesser effort, there is an order relationship. So even if there is nothing like that, you can just define, if the values are exactly the same, then the distance is small. If the values are different, then the distance is like 1 unit or something. You can define it that way. Yeah. Yes.
Yeah, just to answer this question, the distance is actually known as Bower's distance.
What's it called?
Bower distance, GOWER. And it was computed back in 1971. What it does is it makes a similarity matrix.
Yeah.
It computes every data point as a similar matrix with one another, and it consists of a vector, and then it computes similarity between two data rows.
Wait. Let's get the similarity later. The question was just about if you have categorical feature vector, what is the distance definition? There's not one, but he's suggesting there's something called Gover's distance, but there are many. Okay, you can literally define anything you want. Okay, but he has some candidates, so probably look it up on Wikipedia or somewhere else. Yeah, but there are many distance metrics that you can use. Good question. Anybody else has a question or a confusion about this quick discussion that we had? Yeah.
Just to understand the first average or the first example where we take text majority, we are saying that say we have 5.
It's going to be 1/3 here.
Yeah. So in that case, we are saying that the influence of the there are
all the nearest neighbors is the same. All the neighbors is the same. Yeah.
So yeah. So if the quantity or the number of neighbors are more, so we say this unknown x prime is to the side of that level.
Yeah.
And in second case, we are saying not just the color, not just the label, but also the distance of the neighbor matters. So that's where we're bringing the K function, that is the distance.
Yes, capital K function, yes.
So can we say that, for example, if there are 5 neighbors, out
Yeah.
of which say 3 are red and 1 is yellow and 1 is green.
Yes.
If the 3 of those neighbors are farther away, like very far
So
away.
actually in this example, ignore the colors. Okay, colors actually don't mean anything because we're talking about numeric situation here. So just think of these as all some gray color or something. These are in the training data. So don't confuse the color, but go ahead.
So if we don't take the regression case, we take the classification case.
Yeah. So let's go back to that classification case.
The influence of the distance is more in that case. So are we adding another parameter called as a distance to define the unknown category of this black dot?
There is this distance which is captured using K, right? This capital K similarity function is saying that the distance between C and this black dot is low. That's why it's 3.5 units here.
Okay.
Whereas the distance between this black dot and green is high, and that's why it's 10 units.
So even in this example, we can see if we don't bring a distance.
Yeah.
So ideally it should be red. The black dot should be red because.
Yeah. If there is no, if K is, let's say, unit or just it's a constant, let's say it's not there at all, then yeah, the counts of reds in the neighborhood is 2 and counts of green is 1. So the class should be red.
Right.
Yeah.
Okay, and if you bring in distance, since we see green is more closer to black dot,
yes,
maybe based on the distance, maybe the weights will change.
Yes.
And it could be turning out to be green.
Yes, that's what exactly happened here. Yes, that's a very good point. That's what we were suggesting here. Okay, and that's why the prediction is still green, which is so. Although the neighborhood shrunk, if you think of the example from 2 slides ago, instead of 9 neighbors, we said 3 neighbors. If it's just 3 neighbors and we didn't take into account this similarity, it would have been instead of green, red would have been the higher number of neighbors, right? So we would have suggested grade C or something. Instead of that, because of similarity, we now still have the same result as before. Yeah. Anybody else has a question or comment? And thanks for that example distance metric. And if you know something or you've used something before that adds to the discussion, please contribute. Okay. Yeah, so here still, this is the weighted average. So the denominator, so if you ignore the 75, 76, and 83, the numerator, the sum of those 3 ratios should be equal to 1. Okay. Okay, so what have we seen? Instance-based learning examples, k-nearest neighbor. So what it does, here's the summary. So what it does is it avoids explicit generalization and constructs a prediction on the fly, in the sense that there's no hypothesis when the data set is available. Okay, there's no when I say hypothesis, think of hypothesis like if you think of linear models or in fact decision trees that we'll talk about, there is some conversion from the data set to some intermediate object. There is nothing like that going on here. So things get computed on the fly when a test query is queried. Okay, when an input is queried. So the data set is represented as a table. It's like within that Python function, let's say called knn, you just do pandas.read CSV, but you don't do anything with that till the function is queried, and then you actually look at, hey, which examples are the nearest neighbors in that table, and then you actually start doing computation. Okay, so that's basically what was the first point. And so it doesn't do generalization. Avoids explicit generalization. So if you think of addition tree, we'll talk about it in a second, and that's where we'll talk about this point again, where you'll see that addition tree does some generalization already. It's a specific technical word, but so far we've not talked about it in detail yet. But it's just a teaser for. We'll discuss that when we talk about addition tree, as well as some later on models. Okay. So okay, it adapts the prediction model well to unseen data, and that's because it's really, as long as you give a good definition of neighborhood, it's really relying on the fact that there is some smoothness or some stability in, like, hey, how do the neighbors behave, or what are the neighbors' scores are, or what are the neighbors' classes are. The query point should have the same value. Okay, so it's relying on that such property. Okay. But at least the vanilla version that we have seen here, so picking those k-nearest neighbors can be slow. Okay, you may have to scan through linearly. So scan through, let's say you have 20 examples, You have to look at first example. Hey, what is the distance from this point to my query point? Is it below a threshold? If it is below a threshold, maybe it's a neighbor. So you can compute all the distances with each of the training data points, and then maybe sort them and take the top 3 or top 9 or whatever. So you need to do something like that. But imagine now the training data having a million examples. You have to compute a distance of your query with each one of those million examples. That's still fast, okay? It's not like it's going to take days. Computers are super fast today, actually. But still, it's slow, okay? It really depends on the data set size. Okay? And you may say, hey, is that the limit of KNN? That's not true. What we've introduced here is like the most basic idea of a KNN, the many variants implemented in different languages and architectures and hardware, and even in chips. So they do kind of do a lot of workarounds. Okay, so you don't have to spend a lot of time for the last bullet point, but if you think of the vanilla KNN that was introduced in the previous few slides, it does take time. Okay. Okay, so now we're gonna switch gear towards decision trees, and we'll introduce them in a second. So you'll see that decision trees are kind of can be contrasted with KNNs in the sense that they do explicit generalization. Not just decision trees, you'll see that SVMs and linear models and logistic regression models, all of them do generalization, but decision tree is the first kind that we're gonna look at, which does explicit generalization. Okay. Yeah.
I have a question in this part. So the second point where we're talking about the unseen data.
Yeah.
So when we develop the k neighborhood model, so basically we are taking X prime and we're saying, okay, we'll take the k neighborhood and then we're going to decide the prediction. Final outcome.
Yeah.
But when we're talking about the unseen data, how do we apply that particular model on the unseen data? So again, I'll have a 1X prime from the unseen data.
Yes.
So I'm going to be following the same process that I was following while I was developing a model, or
so while developing the model, you're not doing anything. You're just reading the CSV file and that's it. Right. So training data is not being processed at all while developing the model. So developing the model is just define this function within which you're gonna kind of retain the whole training data. At query time, as it like when you need to make a prediction, now on the fly, you'll say, hey, now let me go back and look back in my training data, which one is the nearest neighbors, and then make a prediction. So all the effort is at the time of when you're given unseen data.
Like when I'm choosing the X prime, again X prime is coming from the training data set, right?
No. X prime is just somebody anybody can give you, right? So think of our black box, right? If you are a machine learning, let's say data scientist, you just create that black box and you just ship it off to other people. Other people will insert X primes and get Y primes.
So basically, in the KNN, there is no nothing sort of model development.
Yeah, there is no model development. Yes.
So basically, directly we are going into the data and we're finding the outcome.
Yeah, you can think of KNN if you think of really in a programmatic way. Think of the KNN function definition, or let's say it's an object from a class. When you initiate in the class initialization step, construction step, you literally retain the whole data set as in your like a private variable, for example. So yeah, you just remember the data basically. So you think of KNN as a thin wrapper around your data. Of course, it's not exposing the data, but it will keep retain a copy of the data so that any given point of time, any new query X prime somebody else gives me, I can, since I have access to the data, I can look up what are the neighbors and therefore what are the labels and make a prediction. So it's like literally remembering everything. Okay. So if your data set is huge, gigabytes, then the KNN, that function or whatever the object will be heavy in terms of memory usage. Yeah.
So one thing that is going to be constant is the value of k.
Yeah, I mean, you can even give that as an input in your function if you want. You can define that way. Yeah. So what is the right choice of k? I think last time we briefly discussed it. So k is equal to 1, for example, will give 0 training error. If you really like, so we haven't discussed training error much. We'll see it today in a few minutes. But we didn't talk about training and test because really when we call building the KNN model, it's just remembering the data. Don't do anything. Only when you get a query, you do something with the data that you have, training data that you have, or the previous data that you have, right? So now, let's say you built this KNN black box and you shipped it off, and let's say a manager or some other teams or the external world is using that model. If these external folks, also have a copy of your training data and just pass the training data as x's, okay, they'll get some predictions, right? For k is equal to 1, and if they pass only the training data as x primes, then there's no in some sense there's no error. Okay, there's no training error if you use the training data itself to pass it to the KNN model when k is equal to 1, little k is equal to 1. Okay, because the neighbor of itself is itself, and I know what the label is, and so they're going to repeat it, produce it. Okay, so training error is 0 when k is equal to little k is equal to 1. But if you increase little k to be, let's say 3 or 9, as we saw in examples, maybe training error is going to be something, positive. But we'll talk about training errors in a little bit more detail when we talk about decision trees. Yeah, but good point. Okay, this is a really good point because instance-based learning is a little bit non-standard, right? I mean, we would always think of, okay, you have data, somehow compress it into some weights. If you think of a linear model or logistic regression, or even in SVM or in decision trees, some representation like a tree representation. We'll see today. But here, there's nothing like that happening. It's literally just giving the data as is, and only at test time you do some computations, which the algorithm we saw earlier. By the way, when you use the word algorithm, it's just a set of, it's a procedure. Algorithm is all the same thing. It's just a sequence of steps. Okay? So even in a function, you could have just a sequence of steps, and that would be just called an algorithm. Okay. Any other questions? Okay. So I'm just contrasting decision tree learning here because I think, yeah, we'll get in decision tree in a second. This slide is actually going to jump directly to probably linear models. But so decision tree, in contrast to KNNs, will do the following. It does explicit generalization, which means the data is not retained. You just convert it into some intermediate object, which is in fact a tree. I mean, this is not a direct contrast with how to adapt to prediction model, but basically it's intuitive to implement, and it's not making assumptions about the data. Okay, as much as, for example, in KNN, for example, you need the similarity function, and so you need to say, hey, is it the Euclidean distance or some other distance for categorical variables? It's unclear, so you'll have to make some judgment there. Although KNN is slow for large number of training examples because it has to do that linear scan. Okay, if it needs to be correct. Decision trees don't have to do that because they kind of forgot the data and have an intermediate representation, this tree. But they may be slow for training or even when evaluating if you have large number of features. Okay, when we talk about large number of features, so think of KNN is really good if you have less than, let's say, 10 features. Okay, and if you have hundreds or thousands of features, then you want to use then you'll have a problem with decision tree. Sorry, when you have less number of whether you have less or more features also influences the performance of KNN. But when you talk about decision trees, all I'm saying is when you have too many features, like hundreds or thousands, then you'll have a problem with training a decision tree classifier. It's not really a problem. I mean, all these problems are surmountable easily with today's computation, but relatively it is a challenge. Okay. And you may say, hey, in which situation can we have thousands of features? One very large, so one very good example is advertising. So if you think of advertising as a trillion plus dollar market, and so think of models being built by likes of Google's and so on. So think of them as really large machine learning models with lots of features. Okay, thousands of features, trying to predict whether what's the right bid or whatever, what's the right price for placing an ad somewhere. Okay, on some web property. Anyway, we'll get to examples later. This is again just continuing the 2D situation. So that's when you can actually visualize decision boundaries. So here we're just seeing the decision boundary when little k is equal to 1, the parameter, or when little k is equal to 15. You can see that when the number of neighbors here are increasing, you kind of have smoother decision boundaries. Okay, decision boundary, by the way, is just a doesn't have to be continuous. Okay, so it could doesn't have to be like just for example one segregation between two classes. It can also have islands and so on. Like you can see when little k is equal to 1. Okay. So anybody confused about this diagram? So the black curve is super important, at least conceptually, because on that black curve, if you get a x prime, like x prime is, in this illustration, there are only two features. X prime has two coordinates. All the training data also has two coordinates in the input. If your x prime is on this black line, then you don't know, like argmax, doesn't have a unique value. So argmax is neither orange nor blue. Both have the same, counts or weighted counts. Okay. So that's the except for the black lines, everywhere else it's fine. It's kind of clear what class you want to be. At least the model says what class you want to be. Yeah. Okay. Let's see. Yeah. So actually, let me switch. There are comments on chat. I guess are there questions? Let me actually check if there are questions. There are no questions. So what I'll do is switch over to the slide deck 1B, okay, and we'll discuss decision tree in a little bit more detail and then come back to this deck. Yeah.
Regarding the example that you said that if x prime is on the black line,
yeah,
what is the output of the model? What does it predict?
It doesn't matter what it predicts. You can flip a coin.
Random,
yeah.
Random output, or is this like if such a situation occurs, we say this is a required answer that the model should do?
Yeah, you can do that. So in your function, if it turns out that argmax is not unique, then you can have a rule saying, hey, let's by default pick one of these classes if you want. So it's all your creativity, right? Whatever you think is right for the business application. Sometimes you can say, hey, I'm going to call numpy.random.random and flip a coin, and if the value is greater than 0.5, I'm going to say grade A. If it's less than 0.5, I'll say grade B, for example. You can do whatever you want. And you can do whatever you want in the sense that somebody else can evaluate and say, hey, is that a good model or not? And that you can do with some held out data set or test data set and so on. But we have not discussed that in the context of k-nearest neighbor so much. We'll talk about those types of evaluations, training data, test data, and talk about decision trees and subsequent models. Yeah, I'm making a switch from the previous slide deck to this slide deck because we'll get into some details about decision trees now. Okay. Okay, so let's we are switching the illustrative example. In previously there was something related to grading. Here it's about so the label is whether the commute is going to be a long commute or a short commute. Okay, so it has 4 features: the hour of commute, okay, local time, weather. What's the weather like? So there are a few values, categorical values, whether there was an accident in that, on the street, and if there's some stalling. Okay. These are just some features related to like traffic, and based on that, whether your commute is long or short. And so this is, let's say you have a table like this, and you want to again create that black box, that function, and so that you can expose it to, you can give it to somebody else, or expose it on the internet, and other people can just figure out, hey, this is my situation, whether my commute is going to be long or short. Okay. So this is very simplistic. Of course, you can imagine making it more realistic in iterations, but for our discussion, let's keep it simple. So let's say you have, let's say, if you have this table and somehow you condense it into, let's say, a prediction model, given some, for example, these 4 values, it's 8 a.m., it's raining, there was an accident, and maybe there's no stalling. What's my, will the commute be long or short? Okay. So these are types of inputs, queries that you can get, this x primes. Okay. And it may turn out that it's not clear. So first of all, this x prime may not be something that you have seen in the past in the training data. Okay. I mean, for example, the first one, I don't know if there's if this entry is there in one of these rows, but in general, I'm just saying that you may see an X prime which is not exactly reflected in your training data. Okay, and so can you describe a model which is, which generalizes? Okay, so which makes these predictions like commute is going to be long, commute is going to be short, but condenses the training data and is able to answer given certain features which were never there, which were not there in the training data. So I guess that's what the sentence here is just trying to allude to generalization. Okay. So we'll directly jump into representation of the decision tree and then talk about how we construct it. So the representation of the tree and how we make decisions using them. Okay, so let's say, so again, you need to think of, I mean, if you want to, if you're a programmer, perspective, it's again a function. Okay, so decision tree function takes an input, and in that function there is a data structure. Okay, so I don't know if some of you have done any computer science courses. So there's this notion of data structure. So one of the data structures is called a graph data structure. Okay, it'll have nodes and edges. Okay, so in particular, one type of graph that we will be concerned here is a tree. Okay, a tree is a directed graph with no, I guess, with no loops. Okay. So so you can see these blue squares are the nodes, and the edges are directed, and they are going from one node to another. Okay, so that's what a tree is, and I'm trying to remember if a tree has n nodes, then does it have to have n minus edges or something? Some of you may check, but so this is an example of a tree. Okay, so that function should have a data structure like this. Okay, hopefully it has been computed from training data. So there's no training data. The function is not wrapping around training data. The function should just have a representation like this tree, and then it's gonna somehow evaluate this tree given that input and spit out an answer and return it to the person who invoked that function, right? So the tree has nodes. These let's talk about how we're gonna evaluate it in a second, like how we're gonna generate an answer. But let's talk about the anatomy of this tree. Each node of this tree kind of corresponds to one of the features. Okay, so like, is the feature leave at, is the feature about stalling, is the feature about accident, is the feature about weather, those are, it's going to be about the feature. Okay, so each node, and each of these edges, okay, these are also called branches, right? Each of these edges correspond to some test that you do on that feature. Okay, so for example, if it's a categorical feature, you say, hey, is the category value equal to something or something else, and so on. If it's a numerical feature, you can say, hey, is the value of that feature greater than 10, less than 10, or whatever. Okay? So you do some tests. Simple test just means an evaluation. Okay, and based on that, you follow the edge. If the test, one of these tests could be, evaluated true, and then you follow that edge to the next node. Okay, so that's what these trees and so that's what these nodes and branches are. Now the tree will have what are called leaves. Okay, just like analogy with real world trees. At the leaves, these nodes. Okay, so you can think of these also as nodes if you want. But leaves, for example, this last edge here is connected to a leaf. It's a slightly different type of node, which is not exactly the feature. It's going to be the labels. Okay, it's going to be the output labels. Okay? So for example, in this case, we're actually looking at classification problem. So the output was only either the commute was long or short, and so those label values will be the leaves. Okay. Any questions about the anatomy of the tree? Okay. So given that structure, if the function somehow can represent this, and it's not difficult to do this with a bunch of lists or dictionaries or tuples, whatever, whichever way you want to represent a tree or a graph. Once you can represent this, given an input, you should be able to evaluate, what prediction you want to make. Okay. So, for example, if you're gonna leave at 8 a.m., then you start at the tree. Given these 4 feature values, okay, you start at the top of the tree. It's called the root of the tree, and then see, hey, first feature I want to look at is leave at. And what is the leave value? It's 8 a.m. Okay, and you follow. So the test, this branch is the only one which has the evaluates to the test being true. So you follow the 8 a.m. branch, and you're directly connected to a leaf node. Okay, so the leaf node is directly saying the value of the output variable. So it's saying, hey, ignore the other 3 feature values that you gave me. If it's 8 a.m., your commute is going to be long. And that's what this particular model is saying. You can improve on these models and so on. So that's how you evaluate. So for example, let's say you're gonna do something else. So if a different input was given, 10 a.m., no accidents, it's rainy, and there's no stalling, then you can follow, okay, you're leaving at, again, it's the same tree. So you see, okay, 10 a.m. is true. Go to the next node. It's talking about stall feature. Let's look at stall. Stall takes 2 values, and we are saying, value is equal to no is the branch that goes this way. And then it's saying the commute is short without looking at the other 2 variables. Okay, so that's how you evaluate it. So in your assignment, you will have to build a decision tree class, or at least a decision tree function from scratch. So you want to really understand how it's working. Okay, so in general, for example, let's actually drop those features that we saw previously, and let's say these are the features. So terrain, unicycle type, and weather. So it's related to biking, and the label is whether you should go for biking or not. Okay, you want to ride the bike or not. And so given this tabular data, you can ask, hey, can you compress this data, basically mold this data? Given this data, can I get a tree representation that I can then pass on to other teams or whatever, so that they can keep evaluating and figure out what decision to make. Okay. Note that so far in this example, the previous example was just saying whether the commute is long or short. Here in this example, we are directly saying, making a decision, a recommendation. Okay, we are saying, hey, you should go for a ride. Many times the mapping from prediction models to decisions is not so straightforward. Okay, so if it is just a, if it's like you're predicting like the risk of a fraud, if the risk level is high, then hey, maybe flag, maybe don't let the credit card go through. Or if the risk level is low, make the credit card go through. Those are simple mappings or simple downstream decisions to make given predictions, but that's not always the case. You may have to make decisions in a much more complicated way, and that's why there's full-fledged courses on decision making. For example, revenue management is a good example. Some of you may be taking that as an elective, if not now, maybe later. So you need to make decisions which are not simple transformations, simple thresholds of predictions. Okay, just trying to clarify that. Okay, so we looked at the anatomy, we looked at how to evaluate the tree given an input. Now let's talk about how we construct it. Okay. Now, again a disclaimer, just less than KNN. We just looked at one variation of KNN. Okay, so there's millions of folks in machine learning area, so everybody has slight variations of what KNN can be. So including the same thing for decision trees, there are many variations of how to define the tree eventually, but all of them have some commonality, which is at the end of the day you need to have a tree structure. So we're going to look at one particular way of construction. Okay, and if you've seen slightly different variations, maybe in 572, that's fine. Let's reconcile that. Okay, so let's start with the way we're going to construct this tree given the data. Okay, so what we're trying to do is now training. Okay, so we want to compress our training data into a tree so that we can use it later. So we're going to do a recursive construction. Okay, which is that, so if it's a recursive construction, and this is an idea from, I guess, again, computer science, a recursion means you kind of call the same function again on maybe a smaller input or a slightly different input. Okay, and if you call the same function again and again, it may turn out to be calling again and again and again forever. That should not be the case. There should be a check in that function, so that something called a base case, so that it doesn't call the function again. Okay, and that's what is called a base case here. Sorry, let me hide that. That's called a base case here. Okay, so if your table doesn't matter what the features are, but the output is saying it's all the same. It's like definitely don't go for a bike ride. Then there's nothing much to do, right? So there's no nothing to do. So you just end there. So that's where you kind of say, hey, there's no recursion to be done. There's no need for calling the same function again, because we are at this point, all my predictions are going to be the same. They're going to say, hey, don't go for a bike ride. Okay? So that's the base case. If all the data is suggesting the same class, in the sense that you don't see the second class at all in that data set, then your prediction given the training data is always going to be the same, whatever class it was. Okay. Otherwise, if that is not the case, now you have this table. Now it's interesting. Now, output side, at least there are at least 2 classes. What you want to do is do 2 steps. First is you want to calculate this as something called a score for each feature. So we had 3 features in the previous in the illustration. So there are 3 features. So each one we're going to compute a score. Okay, and so now we have 3 numbers, 1 for each feature, which are scores, and then we're going to use that to split the data. Okay, we're going to pick the feature with the highest score and split the data. And then once the data is split, we're going to call the same tree construction function again on each of the 2 split. Let's say we get a 2 split, then on each side of the data that we split. Okay, so I guess let me recap. So the 2 steps are: first compute scores for each feature, and then pick the feature with the highest score in my version, but it could be lowest score if you want to change the way we score it and so on. But in this version, it's going to be highest score, and then that's the feature that we want to use basically for the current node essentially. And then we're going to, given the original data, we're going to split it into 2 data sets and then pass it on to the next calls. Okay, next time we're going to call this thing. So for example, you can imagine that once we split, maybe one side of the data all has the same class. Then we'll hit the base case and we will not call this splitting procedure and so on at all on that side. Okay. So let's actually look at it. So here's the data. So let's start with the first feature. So we are just starting out. So there's nothing, no tree at the beginning. We just have the data set. We have 3 features. So we'll start with start with the first feature. And the first feature turns out is only taking 2 categorical values, trail and road. Okay. So then we know that. So what we're trying to do here, by the way, is for each of the 3 features, we're going to get a score. Okay. But to get a score, this is how we'll do it. Okay. So first, we'll pick the feature terrain. We have 2 values that we can take. For each value, we can look at that subset of the data and look at the labels corresponding to that data. Okay. So for example, for the road value, let's look at all these yellow highlighted rows, and let's just tabulate. In particular, this is also again a binary classification problem. The output space just has 2 output space. If you think of a set, the set has size 2. Okay, either go or no. Either yes or no. So we look at the counts of how many times it was yes and how many times it was no. Okay, so yes was 4 and no was 1. Okay. Similarly, for the other value that this feature is taking, we're going to count the number of times the output value was one class or the other. Okay, so all we've done is pick the feature, all the values it takes for each value, pick the rows and look at the outputs. Okay, so there's just some sort of a very quick computation, right? You can just do, you can easily program it, right? So we did this. Now let's actually repeat the same thing for the other features. Okay, so for unicycle, again, there are only, turns out in this illustration, they're only taking 2 values, normal and mountain. So for each one, we're again gonna look at, okay, let's look at normal and all the rows corresponding to normal, and then look at the outputs and tabulate them. So for them, yes is 4 and no is 0. And similarly, when unicycle value is normal, yes is 2 and no is 4. Okay. So you can see that there's 10 rows, and similarly here it's 10 rows. Okay, so all this sum 4 plus 1 plus 2 plus 3, so the same as 4 plus 0 plus 2 plus 4, for example. Okay. And similarly for weather, the weather is a categorical value, a categorical variable with 3 values. For each one, you can again figure out what is the yeses and what is the proportion of no's. Okay, so why are we doing this? This is just an intermediate step. What we want to actually do is compute scores. Okay, the scores that we want. Okay. And based on the scores, I'm going to pick one of them to be the starting, one of them to build my tree. That's what I'm trying to do. So first of all, base case is not true, right? Because there is a variation in the output label. So base case is not a true. We are already in this situation where we want to pick pick one of these features based on whether the score is high or not. Okay, so let's go compute scores based on these tabulations that we've done. Okay, so the same tables, so the same I guess computations are replicated here. So it's just the same as the right-hand side column in the previous slide. So now what we want to do is from these counts, we want to compute score, compute S score. Okay, and we'll just talk about one here, and I'm going to allude to other ones that you have seen in maybe other classes later. So we want to compute a score for each feature. So the way we're going to intuit about it is that if we stop, if we stop in the sense of the tree construction procedure, is just that we pick one feature each, and for each feature we computed these types of summaries, these types of counts, and we want to stop here. Okay, we want to stop here and just try to define a decision tree. You can think of these three as candidate decision trees, okay? Because they already have one node, two edges at least. Okay, we have not defined what the leaves are, but we're going to do that in a second. But if you wanted to stop here, we already have at least some candidate from which I can define like my final decision tree, for example. Okay. And clearly they're not decision trees because I need to attach to each of these two, for example, branches, a leaf node which says, hey, which class, what is the class? Okay, so if I do that, then it's actually a candidate tree that I can say, hey, here's my decision tree, and I don't, I can terminate, right? So the way we do attach a leaf node for each one is again a simple heuristic, very similar to what we were doing in KNN, actually. So we look at, okay, here we want to attach a leaf node, and the leaf node, remember, has to be one of the values of the output class. Okay, so one of the values of the output variable, right? Either you go or don't, either no or yes. You can see that here, the number of yeses is 4 and number of no's is 1. So you can just say, hey, majority is, there are a lot more yeses than no's. So I'll take the argmax, basically. The argmax of 4, 1 vector is the first coordinate, and that coordinate corresponds to yes. And so I'm going to say, hey, here the leaf node should be yes. And similarly for the right-hand side, we'll just say, hey, the argmax is no. Okay. So and so what I've highlighted here in green are the argmaxes. So think of the green part to be the leaves, candidate leaf nodes. Okay. So that in that sense, I have 3 trees. The trees of depth 1. Depth is just the number of layers that you can have in a tree. So think of so this tree is depth 1 because from the root or from an internal node, you're directly getting the leaf. So there's no other internal node. There's no other feature node. And so their depth is 1. If there was a feature node and then one more step later, there was a leaf, then it will be depth 2, and so on. Okay. So depth is just a property of a tree. Okay. Just to kind of say, hey, the tree is too deep, right? That's all it means. So these are the 3 candidates. Now let's talk about training error. Okay, so now we're going to define this quantity training error, which is the average error over the training set. Okay, so and what is this error? This error is just the number of times I have I make a mistake in prediction. Okay, so in the sense that on the training data, okay, let's say I have this tree, then because this tree is going to always say yes if terrain value is equal to road, right? How many errors will it make? Okay, so if it says yes, I know that there's one more row in my training data where the answer should be no. Okay, so which means I'm making at least one error right here. Right? So similarly, if the terrain is trail, I'm saying no, but in training data is actually two more observations are there where it's actually should be yes. So I'm making 2 more errors here. So okay, so that's what is the definition of training error here. Okay, so so the training error for the left most tree, this is the degenerate tree or decision stump. There are different names for this. Is 1 error here because I'm saying yes. The green ones are actually the tree's leaf nodes, whereas in reality, I know there's 1 row which actually has no as a example. So there's 1 error here and 2 errors there. So 3 out of 10. 10 is the number of rows we had in our training data. Okay, so in our illustrative data, there's only 10 rows. Okay, so there are 3 errors being made by this made if I under this candidate tree. And similarly, there are 2 errors being made in under this tree, 2 errors because in the left side there is no errors being made. On the right side, my majority is no, whereas the minority class yes, the 2 rows which actually correspond to yes. Okay, so that's why 2 errors by the unicycle feature and 4 errors by the weather feature. Okay. Is this clear for folks? Okay. Oh, we started at 3 or 3:30? Okay. Yeah. So let's actually continue a couple of more minutes and then maybe take a break. Okay. So we just did error counting, okay, and normalize it by the number of observations. And so you don't worry about the normalization. So we did error counting, okay. So 1 minus that error counting is like counting the accuracy. How many times did you match whatever was there in the training data? Okay. So for example, instead of 3 tens, you can say, hey, what is 1 minus 3 tens? It's 7 tens, and that's going to be my definition for training accuracy. Okay. So the reason why we are using training is because we're just saying, hey, how well does this these candidate leaves that I'm proposing match the training data. And so they match pretty well. They match 7 out of 10 cases, 7 out of 10 rows. They are going to give you the right answer if you pick yes to be the left side and no to be the right side leaf node. Okay. So what you do is then the idea is to pick so think of this training accuracy as the score for each feature. Okay. And so we're going to pick the feature with the highest score. Okay, so 8 by 10 is the highest score here. So we're going to pick unicycle as the starting point of our tree construction. Okay, so we started unicycle, and so what we're going to do is pick up what previous construction that we did, counts and everything, and then we're going to split the data. Okay, so split the data. Actually, yeah, split the data into data that involves unicycle equal to mountain, and split the data into data that involves unicycle equal to normal. Okay, and we know there's 4 rows which involve mountain and 6 rows which involve normal. And we're going to now do recursion, right? Now imagine on the left side, the 4 rows which involve mountain. Okay, I don't know if I have that picture. Yeah, on the 4 rows which involve mountain, if you look at the output labels, they're all the same. Now we hit a base case here. We don't have to call for picking another feature, scoring them, and taking the highest score feature and all that. We don't have to do. And so nothing to do on the left side. Okay, so it's important to note this. And then on the right side, you can see that under all the rows which correspond to normal, there is some variation in the output. Okay, so that is good. So which means we can do the recursion. Okay, we don't hit the base case. We can do recursion, and we can examine the other features. Okay, so that's what we're going to do. We have already exhausted this feature unicycle because on the left side it's exactly taking one value, on the right side it's exactly taking one value, and those 2 values are the only values possible for this feature. So we have exhausted it. So we're going to pick the other features possible, which is terrain and weather. Okay, so on the left side, nothing to do. On the right side, we have terrain and weather, out of which we can again score them, figure out which one is the highest score, and use that as the next node. Okay, next internal node. So let's look at that. So terrain, it takes 2 values, trail and road. And again, you can look at there are 3 rows with trail and 3 rows with road, and you can again see how many rows have value yes and how many rows have value no, and so on. So these are the counts. And similarly for weather, you have a similar set of counts for the 3 values. Okay, and you can actually just eyeball how much of error you're having. You can see that the majority or the highest number of counts is for yes, and so you have 1 error here if you think of yes as the potential label there. And on the right side, if you think of no as a potential label, there's no error. So it's like 1 by 6. Okay. Similarly here, you can see, here it's unclear, like irrespective of what you pick, you will have an error of 1, and irrespective of what you pick, you'll have an error of 1. And so you have 2 by 6 as the error here. And so you can flip that and get accuracies. And And so based on these errors or the inverse of them, basically accuracies, you can pick terrain as the choice. Okay, so pick terrain as a choice, and again you hit a base case here, so where all the output for the right hand value, which is the terrain is equal to trail, it's all the same values, so there's nothing to do there. For road, again there's some variation. You can, and the only other feature left is weather, and so you use weather, and you just pick one of them. For example, for yes versus no, you just pick one of them, and this is the full tree construction. Okay, because beyond this you don't have any more features to use, and so you stop. That's also, I guess, a base case. You don't have any features to work with, so you stop. So any questions about this construction? Okay, so let's take a few 10-minute break. Let's assume at 4:43. Okay, let's resume. Okay, let's resume. I want to quickly comment about assignment 1. Just the basic details so that everybody is on the same flow, because we're going to repeat it 5 times. Setting 5 times as in 5 assignments. It will have the same procedure. Okay, basically all solutions should be a single. Although you're working in a group, you should somehow eventually have one artifact, which is one ideally an IPython notebook or a Jupyter notebook, and a PDF version of the same notebook. Basically, you can just do save as or export as PDF. The notebook and the PDF should have the outputs. So don't scrub the outputs. Okay, so in Jupyter Notebook you can clear all the outputs, so don't clear that when you make a submission. And so those two you want to upload it to Blackboard. So Blackboard already has the upload links. What we're trying to finalize is the group uploading part, which is so that if you can let us know the group ASAP, then one of the team members can upload, and it will reflect for all the other group members as well. Okay. Any questions about this process? Now, with respect to collaboration, I don't know how many of you have used the notebook version of Python REPL, or if you're using Spider plus directly writing Py files. So we prefer IPython notebook ideally, but if you really want to do a Py file, I would suggest not, but if you want to do it, certainly. One potential way to do this, if you're not worried about using a third-party source, a third-party resource is Google Colab. So we use it in another course of ours, deep learning course. So it's a hosted service by Google where you can work with Jupyter notebooks, but also you can share between your group members so that everybody can see the same notebook or clone and so on. Okay, so you can use Google Colab. So I think it's just called. So that's the URL. So you should be able to see. I'm not signed in, but you should be able to see and make. So this is actually just a. So if you want to write text, okay, in some of the answers may want to write text, you can make a cell like the Jupyter notebooks and Colab notebooks. They're all very similar. So you can have a text cell, or a markdown is just a formatting of the text, but you can have a markdown or a non-code cell or a code cell. And code cell is something like this. Like you have a variable and you're setting into some value and printing it out. But you can also have a text cell, which is, I guess, this one is also text cell. Okay, so you can work with text as well as code in the same document. So okay, so and then you can export it appropriately. Like I guess download the notebook if you want, and or you can print it, and you'll have the answers there, and so you can upload it into Blackboard. Okay, if you want to use this, you don't have to use this. You can have your own local Python installation on your workspace, sorry, on your laptops, and you can do the same work. Okay. Another way to work is to try to solve, if you really want to challenge yourself, try to solve the questions individually in the group across each group members, and then try to collate and discuss the answers and get to one answer. Okay. So that is a little bit, I guess, it's like literally doing the assignment individually and then just merging the answers, but it still gives you a lot of wiggle room to actually work through things. Okay. And if you're in a group, if you don't work through things, you will miss out much of the learning here. It's really hands-on, and especially if you're a beginner level Python, I'm sure through these assignments you'll become an intermediate level Python user. So that's another perk. So try to work individually. Ideally, you're highly encouraged. So any questions about this logistic detail? Okay. So if not, let me switch back. So I think, yeah. So we reached up to this point, which is an example. So it was only a 10 example table, very small illustration, 3 features and so on. And this is the tree we got. Okay. So this tree, the question is like, this is the tree. Okay. So from the training, data, we condense to this tree. Does this tree, what is its training error? Okay. So that's the question. And you can actually just eyeball and answer that, but that's a question I want to see if some of you can see and try to answer what is the training error of this model or this tree. So what you need to focus on is the leaves, and based on the leaves, do you have a sense of what is the training error of this tree? Yes. So that's the correct answer. But a good quick check. So it's basically just because the majority in each of the leaves, which is the leaves is supposed to be the label value, which is colored in green, and you can see that there is no in those leaves, there is no leaf which has a gray value. Okay? So the gray values are all 0, and that's why the training error is 0. See, in the previous slide, I thought I saw 1, but probably not. Yeah, here there is a 1, and that's why there's a training error 1 by 10 here, but here there is none. Okay, so then I guess natural question is, are we always guaranteed to get a 0 training error?
No.
Why is that? Any one of you want to just quickly answer? Why can't we get a 0 training error using this process? Yeah.
If there are no more features, yes.
Yeah. How does it prevent us from getting no
If
0
there
training
are
error?
no more features, then we cannot
Recurse?
make more tree out of this
Yeah.
table, and the error won't be 0 because it will be the least node we are reaching.
No, we could, here we have exhausted all the 3 features, and here we do have a 0 training error. So it's like, but not always is what you're trying to say. Okay, that's a good point. Anybody else?
Insufficiency of data.
Insufficiency of data, by which, what do you mean by that?
So basically, whenever you're building a tree, so as she said that if we have certain other features, so
Yeah.
we can reach till a point.
Yeah.
But if obviously the data is not sufficient and there
What is meant by sufficiencies here?
Sufficiency means obviously if you have more data, you can refine a model. You can get a better defined model.
So when you say more data, you mean more rows
more
here?
number of instances, more number of observations.
Okay.
So basically, if I add one more observation, and
yeah,
that observation can be completely different from all these above, like 10 combinations. So
yeah,
obviously, I'm not going to get a pure results
Yes,
that we're
yes,
getting here right now.
yes.
So,
So that's okay. That's a good point. So actually, for example, if you had one more row which had a contradiction such that here no is equal to 1, okay, it flows through exactly unicycle normal, terrain is equal to road, weather is rainy, and go for a ride happens to be no for that, then you'll have a 1 here, right? And you've already exhausted the features and you have 1 there. So potentially having more rows is bad because your training error is gonna go from 0 to non-zero. Okay. Yeah, so there are many ways, training error need not be 0. Okay, I guess this is the related to what you call sufficiency, but is that a question? I don't know. So the thing is, I don't know if it's a personal message or not. I need to mention that. Actually, it's not a personal message, so let me just share anyway. Okay, so folks on Zoom, don't send me direct messages because it's shared in the class. But yeah, so you can certainly send message to everyone like this. So, so Prerna's point here is recursion is time consuming. That's fine. And so you may want to trade off that with training error. Okay, so we'll consider that later. Okay, so this is something else. If the question was even fundamentally, would the training error be 0? And there were already a couple of answers that, hey, training error need not be 0 even fundamentally. Here, looks like the point is about, you can probably, if you have too many features, maybe instead of getting to training error 0, you can stop early. And if you stop early, you may have training error. Okay, so that can happen. It's a good point. But we'll get there. So yeah, so he in this slide it's a very contradictory examples for the same feature values. There are 2 different answers. And the question is, when can this happen? Why would there be 2 different answers in the training data for the same feature values, right? What do you think?
different DXAs, maybe. Like basically, there is one column is not basically present here, and that's the column that can explain the final outcome difference.
Yeah, so there are several ways in which you can have 2 such a contradiction here. One, as she said, is maybe there's another column and they differ in that column, and based on that, it's whether you go for a ride or not is a different answer. Or in general, the output here, output label could be stochastic, it could be random, could be random given the input features. Okay, and we'll see this type of idea, the statistical idea, build up when we talk about linear models today and next class. That in fact, we'll assume in linear models, for example, I will make that assumption that the output, let's think of regression, we'll assume that the output conditional on the input is a Gaussian distributed random variable. So of course, if it's a random variable, then it will not have an exact, every time it's not going to produce the same Y. Okay. Here, similarly, instead of Gaussian, you can think of a discrete distribution if you want, but output could be random. And so for the same feature vector, you could have something different. But yeah, as you said, you could have missing features because of which they're different and so on. Or it could be also just data entry error. Okay, that we cannot rule that out. Okay, so now let's actually start talking about, and this is actually an important point that she raised, that the base case should not be just that all data belongs to the same class, but it can also be that all the data has the same feature values. So that's when you stop. Okay, so for example, here the data has the same feature values. Of course, the output is not the same. It's still no and yes on that side of the that subset of the data, but the feature values happen to be the same, and so you don't have the recursive mode. So it's just we're just trying to define the base case, expand the base case definition a little bit more because something like this can happen. Okay, so that's captured by all the data has the same feature values. Then maybe there's nothing to do because it's all the same. You have the same features, but you're producing different outputs. There's nothing much to do. I guess the next question is, do we always have to go all the way to the bottom? And this is something that I guess the remote student mentioned. All the way to the bottom just means, do we have to continually create the trees with internal nodes and leaves till we hit these base cases? because if we hit these base cases, that's when we get the three nodes, and that part of the tree is constructed and is done. Okay? Right? Each part of the tree is done only when you hit these base cases, right? So do we have to go all the way to the bottom? The answer is, of course, probably not, because even if you go all the way to the bottom, anyway, training error is not 0, and it's first of all unclear whether we want training error to be 0. But here's so we'll try to kind of, and some of this you already know, that we may want to kind of regularize and not create tree all the way to the bottom. Okay, so that's what we're gonna work towards. So here's here's the same example with the same tree. Okay, and the question is, why not just this tree instead of the previous tree? Okay, the tree which is this, which is below, only has a depth of 1, and here this tree has a depth of 3. Okay, depth means how many edges are between from the root node all the way to the leaves. Okay, the longest path, how many edges are there in that. So why don't we stop directly at the once we construct the first root, right? Why not this tree, and why that tree? Right? Why recurse all the way to the end? Right? Because we know that when we did this unicycle based splitting, we did compute the training accuracy number, and that was pretty high. I think it was probably 80% or something, right? And so, whereas the tree at the top has an accuracy of 100%, I guess, depending on if one of the rows had a contradiction or not. So why not prefer the second one versus the first one? And this is the motivation. This is the motivation that we can kind of explore, whether whether we can stop early, okay, in tree construction. Or work with, try to terminate the recursive procedure early. Yeah, I don't think we need to talk about that aside because we just saw that. Okay, so we'll talk about that, the preference between those two trees that we saw in a second. But again, what if we had a data set like this, okay, which had again the original 3 features, but now there are some extra features. Some of them are probably irrelevant, like this jacket and machine learning grade. And so what would the tree look like? And tree would have a lot more potentially internal nodes, a lot more branches, or whatever the outgoing edges. So adding features increases the potentially the tree size. So what we're trying to say is that when you do this recursive construction, you may be erring towards overfitting. And this is a word that we're introducing now. I mean, you might have seen it in other courses. So overfitting for us, and we're going to iterate over this definition a few times over the lectures. But for now, overfitting occurs when we bias our model, our structure, in our tree structure, too much towards the training data. Okay, and so this tree here at the top is an example which is not overfit, okay? Whereas the 3 depth tree that we had constructed before could be overfit. Okay? And so our goal is to learn a model. So although it's boldface here, a general model, so a model that can generalize. Okay, so it is not tied down, only to the training data. Okay, so because the previous tree construction that we did, it is very, we were looking at training data and we created the tree as much as possible. That's like too much bias towards the training data. Whereas what we want is a structure, a model, which is a tree structure here, is hopefully is general enough. Maybe there are other patterns, maybe other feature vectors that appear, as unseen cases where we want to have good prediction, right? So we want to have some generalizability of the data, and so you don't want to be too tied to the training data. That's all I want to say. So here's an example. So this is a plot of size of the tree versus the accuracy. Okay, this is not the same illustration data from before, but you can see that. So this is some unknown data set. So you can see that as you increase the size of the tree, the accuracy is increasing. And you can see that the accuracy is kind of plateaued at 87% or something. And that's because exactly because of the cases that you mentioned. Even if you try to create more and more nodes, you may not get 0% error or 100% accuracy. Now, the question is, do we want to always, like, do we prefer a tree with 90 nodes, or do we prefer a tree with, let's say, 30 nodes? Okay, that's the question. And as we just alluded to, the 90 nodes one is probably super biased towards the training data. Okay, and the reason why we don't want to do that is because we have another metric that we cannot measure, while training, but we may have a proxy for it, and we'll see that later. We have another metric that we really care about in the real world. So we don't really care about the training data metric. Okay, that's just a proxy. That's just an intermediate, guiding score, guiding, I guess, reference. But what we really want to do is create that function which can do well with unseen examples and so in the real world, right? So from the training data, we want to learn a model, this blue circle here. But what we really care about it, how does it do on this red box, which is all this potential training data, potential testing data, potential unseen examples that come out. Okay, and so we want this blue thing to be doing well on that. And so you can see that in this plot, what we've added is this dashed line, which is the performance on test data. Okay, now just for our purposes, just think of this as data that was not used for training. Okay, and that's only being used to kind of give another metric, kind of proxying this red box. Okay, hey, you created a model with 50 nodes, you created a model with 80 nodes. How did it do on this data that, this held out data that was only used to report this dashed bar? So you can see that the accuracy on this held out data or test data increases from, let's say, 65 to 75%, and then it kind of keeps decreasing, or whatever, plateaus or decreases. Okay, so you are actually, by biasing yourself more and more towards the training data, you're actually doing worse in terms of this test data. Okay, so that's what we want to illustrate. And so this is the motivation for doing, not picking the tree and not finishing the recursion all the way to the end. Okay, so we want to prevent this overfitting, but we only have training data to work with. So, and it's either you can use the training data. So we're already using the training data to build a tree, and we want to prevent overfitting. So how do we get that signal to say, hey, maybe we're overfitting, we need to stop, right? So it's unclear where we get a signal. You can just use rules of thumb. Okay, that's one way to kind of prevent yourself from overfitting. Or you can use only part of the training data, keep another part of the training data separate and try to see if it can proxy test data and so on. So there are many ways to do that. So here in this slide, we're just suggesting, why not just use rules of thumb, or some domain knowledge, basically non-data driven preferences that you can have. For example, hey, why don't we have a base case where we define, hey, what if so we had these two conditions already. What if we also add, let's say we already have a depth 3 tree, let's stop. Okay, or we already have a depth 5 tree, let's stop. That's a preference that's not driven by the data. It's just a preference that you are giving to kind of hedge yourself against overfitting. Okay. Or, I mean, there are many other points. So another point is, for example, when you only have a certain number of examples remaining when you're considering the split. Okay, so for example, if they're less than 10 points, then maybe you don't want to split anymore. Okay, in that branch of the tree, in that portion of the tree. Or you can also stop when you say, hey, accuracy is already 80%. I know that it's not possible to be more accurate than 80%. Then probably I should just stop here. But these are all extra domain knowledge that you bring into the table. The last point, development data is just exactly what I was saying earlier. When you have training data, maybe you can hold out a part of the training data and do something with it to get a sense for whether you're overfitting or not. Okay, we'll talk about this later on when we look at some other models. Another way to prevent overfitting is to first build a full tree, whatever you can do. Just follow the base without inserting your domain knowledge. The full tree is, in our illustration was this, and then backtrack and try to delete parts of the tree. Okay, in a process which is called pruning. Okay, so basically once the tree is built, now you go back and say, hey, maybe this weather node should not be there, and drop it. Okay, so that you delete it, and there are some criteria that you can just. So tree is a nice data structure where or a nice representation where who the parents are, who the children are, and so on. So you can actually navigate across a tree nicely, and so you can start from the leaves and see, hey, what is the bang per buck which this split is giving compared to if the split was not there. So basically, just think of it as this way: if the split was not there, if let's say the weather was not there, the tree is of depth 2 and it has some training performance or some training error or some training error. If the split is there, there's some other training error. Is the delta big enough? Okay, is the difference big? Is the difference big enough? If the difference is big enough, maybe we should retain it. If it's not, let's prune it. Okay, that's one example. Yeah. Cross validation for pruning. Yes, so that's actually something that we will not discuss right now. This last point here. So cross validation is about the underlying idea is exactly this, to kind of get a sense of this red circle or a measure which is not related to training performance measure. Okay, you can use cross validation to make decisions, right? Like how much depth to have and so on. But we'll talk about it in detail a few lectures from now. Yeah. So far we are not discussing that, but that's a good point. Yeah. I think. Yeah, this is what I said. We're not going to look at the exact details of how to prune here, but I told you the intuition. I basically prune back leaves that are too specific or not giving enough, enough improvement in your performance. Okay, so now we're just finishing up decision trees. One treatment. There's so many variations here that that I'm sure some of you in the audience have tried out in your assignments from before or elsewhere. You probably already are familiar with this. One extension is, hey, what do you do with non-binary attributes? Okay, so far we have seen at most 3 features. I think weather had like 3 features, but the other 2 had like were categorical and only had 2 features. We can also have numeric columns. And so how do you deal with both numeric columns, which is I guess real valued, and also features which have too many categorical values? Okay, so how do you deal with them? Here's a potential. I mean, there's no hard and fast rule of one is better than the other. Here's one potential approach for at least when you have features with. I think there's a comment in the chat, but we'll get to that in a second. So if you have features with too many values, then you can either do an n-array split, which is what we saw, 3-array. So n-array is just a shorthand. Okay, so it just means make n splits where little n is the number of values that you're taking. So that could be too many, right? So maybe some categorical value, let's say, corresponds to country, and then there are 180 countries or 200 countries. So there's too many splits, too many branches going out potentially, right? So instead of that, you can probably do also multiple binary splits. So for example, you can say, hey, country US versus non-US, country in the North America versus non-North America. So you can binarize that and make a split as well. So okay, this is gonna. I mean, this is not enough, right? If you really need all the splits for all the countries, then it will grow. It will be a huge portion of your tree, the right-hand side part. Or you can do one level, split over all the countries. That's another approach. Okay, and you can already see some issues with either approach. So, but that's one way to deal with it. Now, real value features very similar to what we were doing, and in fact, this is although we are brushing it away as we can do this, but actually, search space is non-trivial. By which I mean, let's say your fare, let's say, is real valued. Now, fare can, let's say, vary between $0 to $100. Okay. Then the question is, how do you split that feature? How do you what is the testing that you can do for that feature? So you can say, hey, fair value. So in the node will be fair, and you can say, hey, one branch is a fair value greater than, less than 20, and the other branch will be, let's say, the opposite condition. you can do this. Okay, so this is, but how did you get to value 20 and not 25 and not 15? That's a search that you're doing actually to get the best choice of the split point. Or you can do multiple ranges as well. That's even more complicated. So in general, working with numeric features involves this consideration of what is exactly the split point itself, in addition to whether you're going to split on the numeric feature. So there's a little bit more work to be done compared to categorical ones. Yeah, and I guess the last point I want to make is about the splitting criteria. We have so far only looked at training error or training accuracy, highest training accuracy or the lowest training error as a way to pick one of these features as the right node to split on. But instead of that, instead of training error as a candidate, you can use something else. Okay, so I think many of you have seen this plot, and I'm going to explain this plot in a second. So the training error is also called misclassification error, and that's this dash with dots line here. Okay, so what is the x-axis and what is the y-axis? Let me explain that in a sec right now. So x-axis is the proportion of so let's say it's a binary split, so it's the proportion of no, let's say I want to simplify it here. So let's say p is the probability, so p is the proportion of incorrects, okay, misclassifications. Okay, so the ratio of misclassification. So remember in when we're looking at one of these splits, let's say unicycle or not, then there was an 80% training accuracy or the 20% misclassification error. So 20% is 0.2 here. Okay, so let's say it's 0.2 here. Whether this plot is symmetric, so whether you consider 20% as misclassification error or misclassification accuracy, doesn't matter. So just think of the plot only going up to 0.5 because it's just left-right symmetric. So what we're trying to say is that, hey, higher, if the misclassification error, we're just saying that if misclassification, so x-axis is basically misclassification error. It's just saying misclassification error is 2.5, misclassification error is 2.5. It's just a 45-degree line. Okay, it's just y is equal to x line. Okay, it's 0.5 when p is equal to 0.5, right? So there's nothing going on with the misclassification error line. The other two lines are just very similar. As a function of misclassification, they can be higher or lower. So it's just a little bit higher. So it's a higher penalty or higher score when the misclassification error is low compared to directly using misclassification error. And similarly, entropy is also similar. It has a higher rate of change when errors are lower compared to when errors are close to 0.5. It's just different criteria. Don't worry about the scale for entropy. If you want, you can divide entropy by 2, and then everything will be between 0 to 0.5. Okay. But these are just entropy and Gini index are two different other criteria that you can use to pick which feature to split on. Okay, when you have multiple competing features. So any questions about them? I haven't defined entropy. I haven't defined a Gini index, but in your assignment you will have to do that. Which seems like, okay, how will I find that information? So I can. So if you want, you can reach out to me or the TA, and we can discuss the definitions. I can even explain entropy right after the class first if you want to stay back and ask about it. But they're just think of them as functions of that data set. How many proportions are yes versus no's or whatever the classes that you have. So it's easy to compute them, and once you compute them, you can get a scoring for whether to split on feature 1 or feature 2. Any questions? So at this point, it's unclear. So there are some good parts of decision trees, some bad parts. The bad parts are actually related to having too many features, or even one feature but too many split choices, and so on. The good part is generalizability. So whether you have a training data of 100 observations or 10,000 observations, somehow it gets compressed into a tree representation, and so you can just work with a tree representation, and in that sense it generalizes. It's also easy to very intuitive in terms of what's happening, because the split points are exactly, hey, is this value greater or less, or is this value taking a specific value? So interpretability is a big thing today, especially with machine learning systems directly interfacing with real people. instead of being behind the scenes, right? It's fast to run because data size doesn't influence how long it takes to make a prediction on an unseen point. As historically and even today, not just decision trees but variations of decision trees do pretty well on tabular data. Okay? They are actually for the low complexity that they actually go quite a bit. So think of the 80-20 principle. So they get 80% of the work done with 20% of the effort, right? So compared to much more elaborate complex models. And relatively no assumptions on the data. Like for example, in CNN, you needed that similarity function if you wanted to improve on like the vanilla equal weighted version. So and that similarity means that you're making assumption. Hey, is it the Euclidean distance or is it some other type of distance between categorical variables and so on? So yeah. Yeah, so I think we discussed this. So let's actually skip that. There are questions. So I don't know whether this is public or private. So let's see. Oh, somebody is typing random stuff. Okay, anyway, so the question is it computationally more efficient to make n-ary splits versus multiple binary splits? I actually don't know the answer. So if somebody knows the answer, you can add whether it's computationally efficient to have n-ary splits versus multiple binary splits. Yeah, n-ary splits may be easier because you're not, you don't have to think about how many binary splits you want and how to binarize those splits. Okay? So maybe a little bit less computationally intensive. Actually, what's the time? Okay, so I think this is where we stopped in the other deck. Okay, so I mean, so let's recap. So what all we have looked at today. I mean, much of it is basic for some of you, but at the same time, there are so many nuances that you should be able to now be very cognizant of. Hey, what if this is, what if we have too many features? What if some what if we have too many data points? What if we want to do maybe KNN as well as decision tree, like what to go with? What are the pros, what are the cons, and so on. Okay, so let's come back to this example. So this is just again an example of with 4 features and an outcome which is great. And if you learn a decision tree here, and let's say you did all the pruning or all the sorts of you wanted to prevent overfitting. Let's say you got to this. Okay, so let's say homework, exam, and based on homework and exam, you're just deciding the grade. I mean, based on homework and exam values, you can figure out what the grade should be, and that's close. That does really well on training data, and also is indicative of when you see unseen data. Okay, so maybe participation and project are not relevant after you prune, or after you try to reduce overfitting. Okay. So this is one tree, but sometimes tree is not the best choice. So let's look at this. So in tree, this is an example of this is the example of what we saw in the before picture in the picture here. So it's splitting on homework greater than 90 or not is not shown here, but and then whether exam value is greater than 74 or 84. Okay, so so homework axis is the x-axis and exam is the y-axis, and you can see that homework was split at 90, and so there's left and right of that, and then based on whether greater than less than 90, and then whether the exam value is at 84 for one side of the split, or whether it's less than or greater than 74 for the other side of the split. So this is how the decision boundary looks like, just to contrast with the KNN decision boundaries that we've been looking at with oranges and blues. So this, this is, basically you'll get boundaries which look like squares, okay, at least in 2 dimension, or cuboids in higher dimension, if you want to imagine. But here is a more messy example. Okay, there's still 2-dimensional data, but here there was, some level of splitting. I mean, this is continuous data, so you can see that X range and Y range, they're not just like before actually, but you can see the amount of splits happening. So you can see squares, so many squares, and so the decision boundary is quite messy, right? So in some sense, this is still overfit. Okay, even if you have stopped at some point, even if you're pruned. And so you could have done something even simpler than decision tree, and that's what is the focus for today, next lecture, where we'll look at a little bit simpler class of models. Okay, for example, instead of doing this, right, this blue versus red, if you ignore this vertical lines, the particular way we're splitting, we could have, if we had the opportunity, we could have split it in a different way, right? We could have split in a diagonal way, and that would have been pretty simple. So, which is exactly written here. Just check whether exam plus homework, the total is less or greater than something. Okay, if it is less or greater, then you assign the appropriate grade. Okay, so that is simpler, and you could actually do these types of splits also in decision trees. Okay, it's not like decision trees are completely incapable of doing this type of split, but that would be like not the vanilla decision tree, but some extension. But this is what we want to go after. Simpler decision boundaries or simpler models, and that model that we show here is actually an example of a linear model. Okay? So let's actually, since we don't have too much time, so this is an example of a linear model. So let's actually come back to the data and look at the table again. So there are 3 features and 1 score. So it's a numeric situation, a regression situation, and the way we're going to motivate linear model is come back to our original discussion from lecture 1, where we're talking about, hey, there's this unknown function f, which relates inputs to outputs, and then machine learning is all the process of coming up with this proxy h function, which either approximates or actually finds the original function, or does as good as this unknown function f, right? So this h function, now we're going to think in terms of this way. So this h function, we're going to kind of parameterize it. Okay, so linear model is a parametric model, and we're going to directly think of this function and kind of restrict it to a certain function type or a certain pattern while defining a function. Okay, that pattern is that this function takes an input but can only do one thing. Okay, it can only have inside the function, it's only characterized by these weights or coefficients. Okay, and it can only take these weights, multiply with coordinates like x homework for x exams, x attendance and participation. You can only do that multiplication with those individual feature values, add them up and return it. Okay, so you kind of define the whole function signature, right? The input is x. You're taking, hey, x has 3 coordinates. You can take each coordinate, multiply with some internal value that function has, and then return it. Okay? There's nothing else you can do. The only flexibility you have is to change the internal values, which are exactly theta 0, theta 1, theta 2, and theta 3. So unlike the decision tree case, or unlike the KNN case, where function signature, or sorry, the function internals, there are quite a few other knobs, like k in terms of KNN, or decision tree, pruning, decision depth, tree depth, and a lot of different things. Here it's just those 3 plus 1 numbers, okay, 4 numbers. So that's the restricted function, hypothesis function. Hypothesis because it's kind of hypothesizing that it's approximating the underlying relationship between inputs and output. Okay, the score. So that's linear model. We will study more in the next lecture from this slide onwards. And if you have questions, I mean, since we did not do too much about linear model, we're going to start from the beginning again. It has really nice connections to many things, including logic regression, ridge regression, and all that. But we'll do that next lecture. So if you have questions about what we discussed today, although it was some of it was elementary for some of you, please feel free to ask questions either here or through Zoom. I think you have or had a office hours with the TA sometime soon. So please, do make use of them, and I'll see you next Monday. Yeah.
So, in this third question,
Yeah, you can keep your laptop there so that I can actually see what's going on.
yeah. So in this assignment third question, A part,
Yeah.
we have to create an express plot for the series object, create a row after dropping the last element, but there is no data.
Create a row is that one.
This one.
Yeah.
Okay, so we have to change the x, y label. Okay.
No, just drop the numpy. I mean, the man thing.
Yeah.
That's all.
Okay, that's it.
Yeah, it's a very simple plotting.
Fine, fine. Thank you.
Yeah.
Is there going to be a question that you
Oh, assignment is already given, right? So, fine. Sharing. You mean like?
like a question?
So these are the questions in the assignment.
Okay. So this is the first assignment we have to do.
First question in that assignment. There's one more. There's one more. And there's one more. So these, what you can do is this is an IPython notebook. If you want to just open it, you can just open it from here, from collaborative research. You can just say, hey, open something. I don't know if I can open it here, but let's say sign in. Oh my God. So actually, you can directly open the notebook here, and if you want to work with it.
PyCharm, download it.
Yeah. Yeah. You can just download it.
But
Yeah.
this one you suggested it's online. It's an online.
It's online because it's easy to share. Yeah. But you can certainly do it in Python. Yeah.
In the project, this you said, no, for the assignment, you have to do all the process, and then again we have to check the overfitting and the accuracy part, like the overfitting, and we have to check the reverse process also, because
Yes.
we do not need the how many nodes will be there. We don't know. No?
You're talking about a specific part in the lecture.
Like the assignment, the question is given. The question is given.
Here, you mean?
No, the assignment which you have given. Oh, yeah.
This is assignment.
Yeah, this one. So, like, if we have to do this, like this through pruning and overfitting,
Yeah.
we have to do the check the reverse process also. Like, for example, there is a question with given data set, training set.
Yeah.
But we do not. But if we are asked like for a test data.
Yeah.
So.
But it's not there. No, there is nothing about.
No,
pruning.
not in this. Like for example.
In reality.
Yeah. So if
Yeah.
to form a model, we have to check the reverse and pruning and overfitting.
Typically, you do, but most people just do cross validation that somebody said, right? So if you have design choices, hey, I want to know I want to know if depth 3 is enough or depth 4 is enough or depth 5 is enough. You can just do cross validation, figure that out. Okay. So you don't have to create a tree, look at its training error, and then prune it, and look at training error. You can, that's one way. You can also do cross validation to figure out, hey, what is the right tree to pick, right? I don't know if I could answer that question, but basically, when you say reverse process, you mean I construct the tree and then prune it, and then I want to evaluate its performance.
Then one by one from the lower level.
Yeah, that's what you do while doing pruning.
Yeah.
You do it, but you do it basically. Yeah, there's no way around it. Either you do it or the software does it automatically for you. But yeah, doing that is a good idea. So the whole point is, why are we trying to prune? We are trying to hedge against overfitting. Otherwise, we could have just not pruned, right? We can just create the whole tree till recursion ends, and that's it.
But it would be biased to one data set now.
To the data set that we use.
Yeah. And
So,
sir, in one question, it was greater than equal to 74 and greater than 84.
Yeah.
So greater than equal to 74 includes greater than 84, no?
Where is that? Oh yeah, it includes, yes. What is the issue with that? This is the one.
Yes, in the end. Above this
Yeah.
one.
Yeah.
So
What's the
I was
point?
saying that while
Yeah, greater than 74 includes 84. Yes.
84 and above all, no. So why not all are right?
No, no. 84 and above is blue, let's say. But it is blue, right? So what is that?
So, but no, I'm saying that 74.
Oh, let's actually look at the rule itself. Okay, so here you're saying, yeah.
Yeah.
So you're saying homework greater than equal to
Yeah.
90. So actually, I didn't write it well. So greater than 90 is, I think this side is yes and that side is no, probably. I don't remember. Let's see which one is what. Yeah, sorry. Greater than 90 is okay. So homework greater than 90, yes, you go to the left side.
Yeah.
And you're checking whether exams is greater than 74. Okay. Yes, then pass. If it's less than 74, it's fail.
Okay.
So
here
yes
comes-
and no are not
Okay,
being
okay.
shown here. So ideally, you should just write homework and then the test conditions on the branches. But
Okay.
you can write it this way as well. It's all the same.
Okay.
Yeah.
Thank you so much.
Professor, I was wondering if you had uploaded these slides on Blackboard or
Oh yeah,
I
these
wanted
slides are
to-
there, right?
I could not access them. So
Where is the? Yeah, so it's right here. So slides are right here.
oh, okay.
Yeah, you click on this and you actually get to this link, and all the slides are here. And if you just don't care about the PPTX, the PDFs are here.
Okay. Thank you.
Hmm.